Hey everybody, welcome back to Pre-Calculus with Mr. Beck. Today we're going to be talking about 8.3. 8.3 is titled The Law of Cosines. So before we get into the Law of Cosines, I wanted to just take a step back and say, where have we gone in Chapter 8? And 8.1, we started talking about right triangle trigonometry. And we did that at the very beginning of the semester in Chapter 6. We went back and said, okay, as you're looking at right triangles, can we solve the right triangle, meaning find all three sides and all three angles? And this is kind of like a kickback to geometry too. Then we took a step further and said, okay, let's show this right triangle trigonometry in application. And then 8.2, we came back and said, okay, what happens if we don't have a right triangle? If we have some other kind of triangle, can we solve the triangle? And we took a couple different cases where we were able to solve the triangle. Those cases were the angle side angle and the angle angle side. Then we also had the ambiguous case of the side side angle to say, can we solve all three of those types of triangles? Today, with the law of cosines, the first question that I have is, why would we need a law of cosines if the law of sines served us pretty well? Well, if you take a look at problem number 1 that I have here, this is a side angle side triangle. So side angle side. With a side angle side triangle, something interesting happens, that if we try to use the law of sines, we would say the sine of A over A equals sine of B over B, which equals the sine of C over C. And filling in the piece of information that we know that A is 4. We also know that B is 6. If I want to use the law of sines with these two portions, we would find that, okay, we have two unknowns. We don't know angle A, we don't know angle B. So it's like, okay, let's use angle C then. So if we try to find the sine of 60 over angle C, then we run into the same situation that if we try to apply the law of sines to any of these cases, then we're not going to be able to solve the triangle because we need to have two things that are corresponding, meaning we need to know an angle and its opposite side. Since we don't have that in a side angle side triangle, we have to come up with a new approach. So this part of the video, or this part of the series of videos, is going to be video 1 out of 3. This one is going to be detailing where the law of sines comes about. So I'm going to start off with the triangle that I have over here and say, with this triangle, I'm going to call this point x comma y in the triangle. We've set it up specifically just so that it makes it easier to derive all the formula comes about. But I have some random point x, y, and I have the base of the triangle that I'm putting on the x-axis. The other point I'm going to be putting on the origin. So if this point B is x comma y, that means this distance right here is x, and this vertical distance right here is called y. If I use my right triangle trigonometry with this information, I can say the cosine of angle C is going to be the adjacent side, x, over the hypotenuse, which is A, which leads me to say that x is going to be equivalent to A cosine of C. And similarly, if I do the sine of angle C, that's going to be the height, which is y, over A, which leads me to say the y-coordinate is equivalent to A sine of C. And this is going to benefit us in a little bit. Right now, I'm going to try to keep it in terms of x and y just to make a little bit of my calculations easier. So going back to this distance we're calling x, that means if I have the entire base of this triangle, which is B, this portion right here, I can call B minus x. And then I'm going to be focusing on this right triangle right here to help me establish what the law of cosine says. So with that right triangle, we have Pythagorean theorem that we can write out. With our Pythagorean theorem, I'm going to start by saying b minus x, that quantity squared, plus y squared is equivalent to c squared. Again, simple Pythagorean theorem. Now, if I want to multiply this out, this is b squared minus 2bx plus x squared plus y squared will equal c squared. And it just occurred to me that was c to the c. We're just going to call that c squared. Now, going back to x is equivalent to a cosine of c. This is where I'm going to do my substitution. So I have b squared minus 2b times a cosine c plus a cosine c, that quantity squared. And then I'm going to substitute the y value in as well, which is a sine of c squared equals c squared. Simplifying a little bit, b squared minus 2ab cosine c plus a squared cosine squared c plus a squared sine squared c equals side c squared. And I don't know how many of you recognize that something's going to happen with that quantity there. But if I factor an a squared out, I'm left with cosine squared c plus sine squared c. And everybody should remember that cosine squared plus sine squared is equivalent to 1. So that leads me to write b squared minus 2ab cosine c plus a squared equals c squared. And just to clean it up a little bit more, I will rewrite it so it's c squared equals, and we like to put it in alphabetical order, a squared plus b squared minus 2ab cosine c. And this is the general formula for the law of cosines, which we can see right here. Now, if you notice, we had this triangle set up very, very specifically, just so we could write it this way. A question gets asked, well, what happens if I don't want to know c squared? What happens if I want to know a squared? Now, I can go through an entire proof one more time, or I can just kind of show the pattern. The a squared will be equivalent to b squared plus c squared minus 2bc cosine of angle A. Or if I want to know b, I could say b squared will equal a squared plus c squared minus 2ac cosine of angle B. What you should notice is, wrong tool. What you should notice is whether you're trying to find side A, side B, and side C, it should match up with the angle that we're trying to find over here. And the other two sides are going to be built into the expression b squared plus c squared. Now, a very cool note that we can add here, and I'm going to show this in blue right here. Very cool note is what happens if we really had a right triangle where, let me draw my right triangle, and let's call angle C that 90-degree angle. Let's call this A, let's call this B. That if, and I'm going to be using this one to find angle C, or side C, that C squared would equal A squared plus B squared, then minus 2AB cosine of 90 degrees, and everybody, the cosine of 90 degrees is 0. So really, we have our Pythagorean theorem that comes out of this if we have a right triangle. So law of cosines could be used not just for any triangle or any triangle with any non-right triangle, I guess is what I'm trying to say. It could also be used with right triangle, where that right triangle has the cosine of 90 degrees, which is 0. So this gives us our opportunity that now we can solve our side angle side triangle, because our goal is we could find all three sides. So this is what we're going to find first. Now, one of the things that we need to remark is the law of cosines is typically used to solve both a side angle side triangle and a side side triangle, which, if you know from geometry, these are congruences. And because they're congruences, there is only one triangle. Now, this is happy that there's only one triangle because if you remember the law of sines, we had the ambiguity, and there's that headache of, is there one triangle, is there two triangles, is there no triangle? Law of cosines guarantees that we're going to end up with one triangle. So I'll go ahead and end this video, and hope you enjoyed this portion of it where we derive the law of cosines. Kind of fascinating, simple. There's a little bit of algebra that we had to work with, but really like it in the end. So stay tuned for video number 2.